an event that we've set up, which is a celebration of a piece of math that got discovered basically 100 years ago. And it was a person who gave a talk about what they discovered at, well, 6 p.m. German time on December 7th, 1920. And so we're trying to repeat that at what's noon Eastern time tomorrow. And so I have to get ready a bunch of things for that. I'll just mention what that's actually about. People are curious. Let me see, let me go ahead and share my screen here. This is the event actually, and you're welcome to come, it's live streamed. What is this about? I can describe it a little bit. Let me not get too far afield on this, but I will describe it a little bit. So, you know, one of the big things that people make use of these days is that computers exist. Now, the question is it obvious that computers should be able to exist? One of the big things about computers is that you can program them, that you can get one computer and you can feed it different programs that do different kinds of things. It was not obvious that that would be possible. If you go back 200 years or something, people would have said, you want to do one kind of thing with a computer, you need to have one kind of computer. You need to actually make a physical object that is an adding machine or is a multiplying machine or whatever else. What happened basically just about 100 years ago is that people realized that that wasn't the case, that it was possible to make a universal machine where just by putting a different program into the machine, you could get the machine to do whatever you wanted, to do any computation you wanted. Now, mostly that was the main place where that was realized was in the 1930s by a chap called Alan Turing, who invented these things called Turing machines, which are sort of simple, idealized models of computers. Computers didn't exist yet at the time. Electronic computers didn't exist yet at the time. But he invented this kind of idealized model of computers that lets you kind of see how you could compute different kinds of things. And the big surprise was that he showed that there existed a universal such machine, a machine where just that one machine, if you fed it different programs, it would compute all sorts of different things. Actually, I have to say that in the, so after Turing machines were invented, people discovered lots of different kinds of ways to set computers up. And the practical ways that computers are set up today are sort of an amalgam of a bunch of those different things. But the main idea is one computer, different programs do different kinds of things. That's what makes software possible, which is kind of a big deal. You don't have to buy a different computer for every different thing you want to do. Actually, I have to say on the subject of Turing machines, I was myself responsible for a little innovation in that, which was, let's see if I can find this and show you. Let's see. Yeah, this was in the nature of a sort of a math competition, actually. The question was, what was the very simplest possible universal Turing machine? In other words, if you wanted to make a machine that could compute anything, how simple could the mechanism inside the machine be? You know, the computers that we currently use, inside their CPU chips, there are like billions of transistors. The question is, can you make a machine which with the right program can kind of do anything you want, but the machine itself is incredibly simple. And it turns out that this is the very simplest possible Turing machine that can exist. And about 13 years ago now, I kind of had guessed that this might be the simplest possible machine. I set up this prize and somebody won it by proving that, yes, this is in fact a universal computer. It's the simplest possible universal computers of this kind. One might say, why does anybody care? Well, if you are, one reason you might care is if you wanted to do computing by just using individual atoms or doing things with a molecule, for example, you might need to have very simple components to make your computer out of. You wouldn't be able to build this big thing with a billion gates and so on that's our CPU chip. You'd have to make something much simpler, for example, out of molecules, and this is a much more plausible way to do that. But anyway, so that was the story of Turing machines, and that's the main place where people kind of imagine that our current idea of universal computers and software and so on comes from. But actually there was a precursor to that idea due to this chap, Moses Schoenfinkel, about whom rather little is known. He invented some things called combinators, which he announced basically 100 years ago tomorrow. Gosh, I could explain to you how combinators work. It wasn't what I was planning to do. I'm happy to do it. The problem with combinators is they're very clever and extremely hard to understand. They're extremely simple in the way that they're set up, but yet in what they do, they're incredibly complicated. In fact, they're so complicated that they can do any computation you want, just like that little Turing machine I showed you, just like any computer we have. They can do any computation they want, but they do it in a way that is really very hard for us humans to understand. And actually that picture there shows just one very simple example of a computation. Starts with this tree and ends up with this tree here. Well, I'd be happy to talk about this if people are interested, but I thought I would talk about something quite different. I thought I would, my main topic is sort of how do you discover new math things? And I suppose the number one way that you get to do that in modern times is by doing math experiments. At least the way, okay, the way that's accessible to lots of people is doing math experiments. And the people, you know, mathematicians, many of the well-known mathematicians, people like Gauss and Riemann and so on, famous mathematicians of the past, Ramanujan and so on, they're kind of, one of the things that they often did was do actual experiments, in the sense that they would try and figure out, something about prime numbers. They would actually work out lots of prime numbers and see what pattern they could see. And then they would try and figure out what might be a theorem that was true about prime numbers based on the pattern they could see. Well, it's a lot easier for us now because we get to use computers to do those experiments. And I've spent a large part of my life building sort of tools that make it easy to do those kinds of experiments. And hopefully many of you have seen Wolfram Alpha, which lets you do all kinds of computations about math and lots of other kinds of things on the web. Some of you might have seen Mathematica and Wolfram Language, which are kind of the kind of professional way that people do use our tools to do all kinds of R&D. The things I'm going to show you, you can try for yourself. In fact, I'll upload whatever notebook I make here to the web, and you can play with it yourself. Really what this is all about is, you know, can you communicate with a computer in such a way as to get it to kind of do what you want? So let's start off. Okay, so we're just going to type very trivial things in. 2 + 2. Okay, works. All right, let's type in like 1,000 factorial. Okay, that works. Actually, let's already do a little experiment. Okay, let's already do a trivial experiment. So the question is, okay, here's a question. Are the digits in a factorial randomly picked from 0 through 9? Do you know? I don't know, actually. If for example, the digits of pi, 3.14159, et cetera, one thing we know about those digits is that so far as we can tell, they're kind of randomly picked. So let's just generate. Let's generate the digits of pi. Let's generate. Let's say just 1,000 digits of pi. That's what I want to do. Okay, there we go. And I have to just say, give me because it's a number with decimals, I have to do that. There are my digits, 314159, et cetera, et cetera, et cetera. Okay, how often do each of these digits occur? Well, we could, for example, we can make a histogram. We could say, let's compare how often the digits occur. So this is showing each bar is showing how many times 0 occurs, how many times 1 occurs, 2, et cetera, right? Okay, so, you know, it looks roughly like they occur equally often. Let's try going to 10,000 digits of pi. Okay, it's looking better. Let's go to 100,000 digits of pi. Okay, now it's really pretty good. Really seems like every digit occurs roughly equally often in pi. Okay, next question. Let's do that for factorials. Let's say we want to make, so up here, we got 1,000 factorial. Let's try saying like integer digits of, let's just say 100 factorial here. Okay, there we have it. Now let's make a histogram of those digits. Okay, it's kind of wiggling around all over the place. Let's go ahead and do that here. Let's say we make, okay, there's a histogram of 100 factorials digits. Let's try, there's a question here. Is there a question? There are way more zeros. Yes, indeed, there are more zeros. Well, let's see. Yes, there do seem to be more zeros here. So let's go try and figure it out. Okay, there's 1,000 factorial. Okay, so what we're seeing is it's roughly equal, except those zeros. There are a bunch more zeros. Let's try 10,000 factorial. Okay, interesting. So maybe this is a general fact. Let's see how many zeros there are compared to other things. So let's see. So what I want to do here, let's do the following. If I can just say counts here, that will give me the counts. Actually, if I say, just to make it easier to read, I'll say key sort this. So sort it by, so that's 0 through 9. That's giving us the counts of the numbers of digits 0 through 9. Okay, so that's 5,800 zeros, 3,200 of these, et cetera, et cetera, et cetera. Okay, let's a little bit more dangerous. Let's do 100,000 factorial. Okay, there we get the result. Okay, so let's take a look. I wonder what that ratio is between the number of zeros and the number of ones. So we can take, if I take this, take 0 divided by that 1, this is going to give me the ratio of those numbers. So let's see, 1.58. Interesting. Okay, so, well, let's see. Let's try doing this. Can anybody figure out what's going to happen? I don't know what's going to happen here. I have a slight guess because I recognize that number as being something that might be significant, but I might be wrong. But let's see. Okay, so let's go. I'll tell you what. We've got a couple of things we could do. Another thing we could do is we could say just to get, well, okay, we can just do the experiment of figuring out how many zeros compared to other digits are there in this. Let me see. So we want to say, so first of all, why are there extra zeros at the end? The answer is because factorials multiply all the numbers together, and every time there's a 2 and a 5, it's going to make a 0, right? Every time there's a 2 and a 5 that appear in any of the numbers that are showing up, it's going to make a 0 at the end. So there are lots more 2s in the numbers that you get between 0 and, let's say, 100, than there are lots more factors of 2 than there are factors of 5. But basically, every factor of 5 is going to give you a 0 at the end. So we're basically counting the number of factors of 5 that we've got in these numbers, as compared to these other digits, which are a little bit harder to assess. But by the way, they'll also be, actually, now that I think about it, there's some part of these zeros will be in the interior of the number, and only some of them will be at the end. So it's probably these ones here, the extra ones are the ones that are at the end. Okay, should we try? Let's try doing the following. Let's try working out. Should we try the ratio of the number of ones to the number of zeros in this number? Now, I think there's a nice function called digit count, if I remember correctly, that I don't use very often. Let's see whether I have to look up its documentation, I'm afraid. Let's see, because the number of D digits in the base B representation of this. Okay. Okay, all right, that's what we want. So it's digit count of, so let's say it's 100 factorial, base 10, and let's say that's zeros. And then the same number, this thing here will be, hopefully, this should be the number of ones in this. Okay, so that's going to give us, really, did I get this right? Hold on a second. Well, I might have done. Let's try here for 100,000 factorial. Let's see if I got the same answer. Yeah, I did get the same answer. Okay, good sign. All right, so let's try doing the following. Now, I'm being a little bit stupid here well, let's recompute the factorials. It doesn't really matter. Okay, so what I'm going to do is I'm going to say, let's make that instead of 100,000 factorial, let's just make it n factorial. And let's just try making a table of that result for n, let's say, goes up to 1,000. Okay. Oh, at the beginning, there's a bunch of weird nonsense because there just weren't any in the denominator. There were no ones in the factorial, so it went crazy. Okay. But let's go ahead and say, let's make a plot. Okay, so that's showing us As we increase n, as we increase the factorial that we're looking at, this is showing us how this ratio of number of zeros to number of ones, what that's doing. So it wiggles around a whole bunch. Every different thing here is a different number, right? But this is now converging to some value. Question is it, well, actually, we don't actually know it's converging. I don't actually know offhand that it's converging to a value at all, but I'm kind of guessing that it is. Let's try seeing what happens if instead of going up to 1,000, we go, let's go, yes, let's see. So let's try doing this. Let's say, let's do 10n factorial here. Actually, no, let's not do it that way. Let's go like this. Let's say n goes from 1,000, 100, 1,000 to 1,000,000, let's say. I'm just a little bit worried this is going to be really slow to compute, but let's give it a try. Let's give it a try. Okay, I'm doing something a bit silly because I'm computing the factorial twice, which is kind of dopey. Too slow, too slow, too slow, too slow. Let's go ahead and compute this instead of, let's just get 10 values here, going up to 1,000,000 factorial. Let's see whether we can do that. No, actually, I really goofed this up. Never mind, bad way to do it. All right, let's do this. Let's call, let's say that we're going to say the ratio of these factorials, we'll call it f rat. Not a very good name, but, and we'll just make that a function there. And now we'll say, what is that ratio for 1,000? Okay, we get the result. Okay, what is that ratio for, let's say, 100,000? Okay, that's the result we got before. And actually, probably what we want to do is say, what's the numerical value of that? Okay, let's just try 1,000,000 here so that we can compute that. How big is 1,000,000 factorial? Oh, well, okay, we got a result. So 1.4699. Okay. So we might guess that this is going to end up at 1.5. I'm not sure. All right, let's just try, just for the hell of it, let's see whether we can get to 2,000,000 factorial. But maybe this gives some idea at least of how we can start to do some experiment like this. I don't particularly know the answer to what's going to happen here. My guess is, oh, look at that. Is that going to converge to 1.5? Hard to know. Can anybody figure it out? I don't know whether, I think this is, sometimes there's some math questions where you pretty much know it's really hard to figure out the answer. This one, I'm pretty sure it's actually not that hard to figure out the answer. I'm pretty sure this one can be figured out. All right, the thing I was going to do was I was just thinking as I was starting this up here of a math question that I don't know the answer to, and which I think is probably quite hard to figure out, but where we can do some experiments and see what's true. And it has to do with prime numbers. So people know about prime numbers, yes? So we can say, if we make a table, let's say, of the first 100 primes. Let's say 100 primes here. Okay, there they are. People know these. And if I wanted to, I could say, I could, for example, make a plot of those values, and we'd see how this is the nth prime. How big is the nth prime? Makes sense? So we can ask all kinds of questions about this. Oh, for example, well, there are many kinds of questions we could ask, but the thing I thought would be interesting to look at is what happens if we kind of iterate this prime number. So in other words, we say prime of n is the nth prime. Okay, that's going to give us a number. What happens if we say prime of 10, and then we say prime of that? We're going to get another number, okay? So the question is if you just start iterating that, or maybe you don't iterate the thing itself, maybe you iterate something based on it, and you say you're going to make prime of prime of prime of prime of prime. So in other words, you start with the 10th prime number, you find out what that number is, then you work out what the 29th prime number is, and you keep going from there. What is going to happen? Now, in general, the way, so we can just think about, we just have some function f, okay? There's a very convenient thing in our language called nest list, and nest list just does this. It just starts nesting things. So in other words, it takes x, then f of x, and so on. So for example, if f was put a frame around a thing, it would do that, okay? But if f is this prime thing, we'll get something much wilder happening. I don't know what's going to happen here. I have no idea. Okay, so let's say nest list prime, and then let's start off with 2, for example. Let's go 10 steps. That may be too scary because the numbers may get very big. No, not too big. Okay, so that's now the nested prime numbers. So that's the second prime, and then the second prime is and then that's getting that number and figuring out that number's prime, and so on and so on and so on. Okay, so we can probably, let's see if we can go a little bit further than this. I suspect these numbers, oh no, these numbers are increasing very rapidly. All right, no, we can't go much further. Okay, so let's try and think about what we might do to make an interesting kind of iteration that uses these prime numbers. So for example, we might try saying, well, here's one. Okay, I got an idea. Okay, so let's say, okay, here's a weird thing we could do. Okay, so prime q tests if a number is prime. So for example, it says 567 isn't prime. Okay, so let's say what we do is we say, I'm thinking what to do here because I'm wondering. Yes. Okay, so let's say, okay, you're asking what is nest list? So nest list is just a function in Wolfram Language, and what it does is it just does exactly this. You take anything, f, any function f, and you put in, and it will literally successively nest one thing, the next thing, next thing. So you could do, like, for example, let's say I say picture of a cat. Okay, so we'll get a picture, hopefully we'll get a picture, a domestic cat image. Okay, there's a cat. And now, for example, one operation we might do on that is we might say blur that picture of a cat. Okay, so we could take the cat, we could blur the cat, and now we can nest list that. So we could say nest list blur, and then the picture of the cat. And what's going to happen? Probably we're going to get something which does not really look, in the end, much like a cat, because what's been doing, it's blurring. What is the software? This is a thing called Wolfram Language that I built for the last 30 years or something. You can find it. All right, let's do a basic software intro here. Okay. First thing to know about our software world, if you don't already know about it, is Wolfram Alpha. Do people here know about Wolfram Alpha? Basically, pretty much all high school kids will know about it, and college kids and so on. But if you don't know about it, I don't know, we can, what might we do here? We might say, you know, plot, let's say x over x plus 2 or something, some simple thing here. Oh, I could even sign in if I really wanted to be swank here. No, I can't be bothered to sign in. Let me not sign in. Okay, so, so Wolfram Alpha is actually the thing that provides the computational knowledge for things like Siri and Alexa and so on as well. But it does mathy kinds of things, and it does lots of, you can ask it lots of questions about the world at large. So you could say, you know, what is the population of Boston divided by New York City? And it will try and answer that, and it'll try and give you some interesting plots and things like this. Or you could ask it something like, something like what is the how about what is the density of water at 26 degrees centigrade? And hopefully it can figure that out and tell you the answer. Or I could say something like, if I want to be a little bit more exotic, I could type in something like, about something like this. That's like a human genome sequence. And it'll go and figure out where that, oh, it says there are no exact matches for that on the human genome. So if I make it a bit shorter, there's probably a match. So this is probably going to tell, no matches for that. I make it even shorter. Okay. Eventually we'll get down to something which has a match. Oh, there we go. So those are matches for that on the human genome. But so this is Wolfram Alpha, where basically you ask it questions in kind of natural language, and it will try and answer them. The thing I'm using here is our Wolfram language, where the idea is there's a definite language that it uses that we've been building for the last 33 years now. That is kind of a language that's set up to let you explain computations to a machine. And it's a language that lets you explain computations about numbers or about pictures or about things in the real world. Like we could say, I don't know, US state capitals or something. That we can enter in natural language, but that'll turn that into some piece of symbolic language that then gives us a result. And we could say, for example, I don't know, we could say something like, well, here's a nice thing to try. We can say, let's try and find a tour that visits all of those cities. Okay, so let's say, and then we could say, make a plot of, let's say, those cities, which were on line 46, and then the last thing here. And let's join it up. So let's see if it can compute that. There we go. So that's a shortest tour that tries to visit all the US state capitals. So I mean, these are all things you do in Wolfram language. If you want to access this, a good place to go is if you go, let's see what the best entry point is, probably a thing called Wolfram Programming Lab. And let me see whether we can get there. Okay, I think this one, all right, here we go. So this, you can just go wolfram.com/programminglab. You say start programming now. Okay, this will give you a bunch of examples that you can play with. This is just running in a web browser. Now you can also, if you're a little bit more fancy, you can go to wolframcloud.com, and you can, you'll have to sign in and get a basic account, which is free, because you're going to store files and things, and then you can go and start doing computations here. So I could do the same, you know, I could do that same 1000 factorial thing that I was doing before, I could do here. And actually, let me show you something. If I take this notebook that I had here, I could, if I wanted to, I could say, I could just say here, publish this to the cloud, and hopefully, let's see, I press publish, and then what it will do is set this up. There we go, it even has a nice barcode. Okay, so we could go here and I could just say, go view that notebook in the cloud. Okay, so this is everything that I was just computing here. You can go find in the cloud. Actually, you can. I'll send you the link right now, and you can go and. But I'll do this at the end, and maybe that way people can play with this themselves. But if you go there, you'll be able to start playing with the things that we were already doing. What it'll show initially is it'll just show you what we did. If you say make your own copy, you can then get your own copy and start editing it and do your own version of these computations. So that's the story. And you know, I would say that the sort of the big idea of our language is to kind of make a language for being able to sort of talk computationally about anything you want to talk about, whether that's numbers, primes, pictures of cats, Pokemons, movies, whatever else. The idea is that the language, or cities, for example, here, that the language already knows about lots of those kinds of things and already knows how to compute things with those kinds of things. And so sort of the notion is to be able to get to use computation to explore whatever you want to explore, whether that's math or all kinds of other things. And you know, I think this is kind of in the big picture, this is sort of the future of how people get to use computers to figure new things out. And people have been using our language for many years in basically pretty much every university and most research labs and things like that to figure out all kinds of things, whether it's in physics or engineering or computer science or whatever else. But the thing that's pretty neat is that, you know, kids can do this too. And there are kids, middle school age kids actually, who are really good at writing code in our language. And once you get kind of fluent at it, it gets to be the case that when you have some sort of question that you wonder about, like we were wondering about those digits of factorials and things, it doesn't take you more than, you know, a minute or something to start answering that question. And that's really cool. And it's something that you guys can perfectly well get to. It's something that it's sort of a superpower that a random set of people in the world seem to have right now, from some sort of old people who have done all kinds of things and then learn this when they're quite old, to people who are really quite young, who know it really, really well. I might point you to, if you're interested in learning this stuff, let's see if I can pull up one thing that might be of relevance, which I can also put a link to. There's a book that I wrote actually, which was actually originally aimed at kids, although it turns out it's also been read by yeah, somebody mentions Jupyter notebooks. Yeah, we invented this notebook thing back in 1988, and the Jupyter people kind of tried to copy what we had, although they have not done a particularly good job, I have to say. In any case, this is and Jupyter is usually used with you can use Jupyter with Wolfram Language, but it's usually used with low-level programming languages like Python and so on. So anyway, if you're interested in learning about this stuff, I recommend this book, which you can find online, and you can find a MOOC version of it, and you can also actually play with it, and it has exercises and things. And if you're really feeling ambitious and you like competition kinds of things, let me show you one other thing that we have. This is a bunch of challenges in our language about lots of different kinds of things. Let's see, there are probably ones here about math. Okay, and you can open the question and it'll ask a question here, and then you get to try and write a piece of code that answers that question. And I know there's some people who've gotten really quite good at this, and there's you can it's a fun thing perhaps to compete with some of them. You don't know who they are. Some of them may turn out to be all kinds of fancy professor types, and some of them may turn out to be kids. Hard to know. We're not just you know, everybody can solve these problems. Well, let's see. Should we go back to looking at our primes, or we could talk about completely other things if people would like to? I think maybe we should turn this over to more of a Q&A, because I think that will perhaps be more fun for people. I mean, I can looked at this before about how to sort of make iterations that are based on just nested functions that are based on prime numbers. Because I bet nobody's ever looked at that in this form before. And something interesting might happen, or not, as the case may be. I mean, I suppose we can try and, how about, okay, I have an idea. How about if what we do, is that going to work? Well, all right, let's see what would happen if we said that the next number in the sequence is, I'm going to write something that's a little bit complicated, but let me just see whether this produces any reasonable result before I waste your time trying to describe what's going on. Oh, bad. Yes, I should have thought of that. That's going to happen. Well, let's see what happens if I do this. That has to be a positive number. Okay. All right, so let's explain what this is doing. This is kind of interesting. Maybe this is obvious. It's not obvious to me. Oh, I see what this is doing. Yes. Okay, what this is doing is it's saying at every step, take the n+1th prime number minus the nth prime number. That means that's giving you the difference between two adjacent prime numbers. And most of the time, that's just giving you, so let's say we say an n there. Most of the time, the difference between two adjacent prime numbers is something small like 2. So let's go this to 100. Okay, so this is not very exciting because what this is doing is it's just going down in a few steps. So like 99, the 99th prime, the 100th prime minus the 99th prime has a difference of 18, but then the 18th prime only has a difference of 6, and so on and so on and so on. So it goes down pretty quickly. But now I wonder what would happen if we did something like this. I wonder what happens if we say, what happens if we do this? Oh no, help. Something bad is happening. Let's see. Well, I'm just, I'm trying to see whether we can get, oh, I see what's going to happen here. Yeah, those numbers are going to get very big again. All right, well, we can, yeah, if people want to suggest things here, that would be great. Or ask about anything else that you want. I can tell you about combinators. I can tell you about other kinds of computer kinds of things. Something about sine. Okay. All right. Sine. Okay. So let's first of all let's remember what is sine. Sine x. So if we have a triangle, right triangle, sine gives us that. Well, actually, if we have a circle, then what? And we are at a certain angle around that circle. So let's draw a circle. Okay, there's a circle. And now let's draw the center of the circle as well. Let's say a point at 0, 0, and the circle. Oops, what did I do wrong? Point at 0, 0, and the circle. Okay, so now let's ask the question, if we put a line that goes to a particular point around the circle. So let's say a line from 0, 0 to the point x, y. Well, actually, let me cheat a little bit. I'm going to put in here, let's put sine t, cosine t, sine t. Okay, and what that's going to do, it's going to make a line from the point 0, 0 to a point with those coordinates. And now let's do this. Let's manipulate here with t going from 0 to 2 pi. And let's see what this does. So what this is going to do, it's going to make a line that winds around like this. Okay. So now the question is, as we wind that line around, as we're moving here, we're changing the angle that that line is at, right? So now the question is, if we want to know what is the y coordinate, how far up is that point as it goes around the circle, we want to figure out how far up that point is, okay? So we could, let's do this. Let's make that line, let's make another line that drops down. Hold on, let me see how I make this. I have to think for a second here. Let's make another line that is going to go from this to cosine t, and let's make that line red, for example. Okay, let's see if this works. There we go. Okay, so see the red line? And that red line is just should tell us just the vertical height that that other line gets to. Make sense? Yeah? Get it? Okay, so now what we want to do, as we move this, as we wind this around, as we change t, as we change this angle here, right? The question is, how long is that red line? Make sense? Okay, so the answer is that red line is this sine function. And we could just say plot that sine function from here. Now, okay, let's do this. So that is telling us, as we go around a circle here, do you guys know about radians? Maybe, maybe not. Radians? Yes?
Yeah.
No, okay. All right, so
Yeah.
let's do this in degrees then. Okay, we'll do this in degrees. Let's forget about radians. They're unnecessarily complicated. Okay, so this is saying x degrees. Yeah, 2 pi radians is 360 degrees. So, but here I just said use degrees. Okay, so now what this is doing is it's saying at 180 degrees here, the value of the sine function is 0. At 90 degrees here, the value of the sine function is 1. Okay, so over here, let me do this. Oh, it'll take me a bit of a mess to give this in degrees. But basically, this is now 0 degrees, 90 degrees, 180 degrees, 270 degrees, etc. Right? So this is saying that at 0 degrees, the sine function should be 0. Okay, that looks good. At 90 degrees, up here, the sine function should be 1. That looks good, and so on. And so this sine function is just, when I say sin square bracket or whatever, that just is the function that represents how high this will be. Okay. So, okay. So let's see whether we can figure out some things about this sine function. What are some things we'd like to know? How about some famous, okay, so if we say sine of 90 degrees, that better be equal to 1, right? Okay, what about sine of 45 degrees? Who knows what that's equal to? People know that?
Root 2 over 2.
Very good. Root 2 over 2 or 1 over square root of 2. Okay, should we see how we can figure that out? If we look up here at 45 degrees, what will we have? We'll basically have I don't know whether that's 45 degrees, let's assume it is. We'll have a triangle here where there's something, a length there, and length there. And it's a right triangle. So if this is equal to 1 and that's equal to 1, then this will be square root of 2. But if we want to divide it so that that's equal to 1, then each of those sides is 1 over square root of 2. Okay. All right. So next question is, for what? We got that. That's in terms of some nice thing with square roots. Okay. Let's work out some other signs. Let's try sine of 10 degrees. I wonder whether that's anything nice. It doesn't know what that is. Let's see what happens if I say this. Let's see. I don't know if this will work. That didn't work very well. Let's see. Let me think. Well, I'm not sure there's a nice formula for this. Okay, so there's the formula for sine of 15 degrees. So it's a little bit messier. We could ask the question for which. Let me think about this for a second, how to do this. Again, I have to look at documentation because I don't remember. I think there may be a way of doing this. How about C also? Maybe trig expand. I wonder whether that will do it. Let's see whether that works. Let's see whether there's a formula for something like this. Yeah, it doesn't seem to be. So here's a question. I mean, so what this is asking for is, in that particular case, it was possible to make that construction with triangles, and we could work out it's 1 over square root of 2. Yes, you could plug it into Wolfram Alpha. That's basically what I'm doing here. This is powered by exactly the same thing that runs Wolfram Alpha. So here, let me just run this for, let's say, in 5-degree increments, from 0 to 90 in 5-degree increments. Let's find out which of them have nice forms. Okay, so not too many of the 5-degree ones. Let's see whether any. Let's try sine of. You know, I'm going to cheat a little bit because I know this more in terms of the 2 pi thing. So normally, instead of using degrees, instead of using 360 degrees, we use 2 pi. And so if I say sine pi over 5, for example, that's equivalent. So pi over 5 in degrees is, let's see, 360 divided by 2 pi times pi over 5, which I should be able to do in my head, but I can't. That's 36 degrees. Okay, so what this is saying is, let me see, if I want to work out, you see, this is where, because I've been using computers to do math basically since I was about 15 years old or something, all of these things, which you guys can probably do instantly, take me a lot more effort. But anyway, there it is. So this particular case, it's 180 over m. Okay, so let's ask the question, sine 180 divided by m degrees, for which values of m can we work out the answer to that? Okay, so let's try that. M goes from, let's say, 1 to 20. This could get very grotesque. No? Okay. Let's see what happens if I say this. Well, actually, if I say this. Oh, that's got a really wild one. Okay, so what this is doing is, it says for some values of sine of some angle here, look at that incredibly wild object that we get out. Now, if we just want the numerical values, they're going to be pretty boring. The numerical values will just follow that line that we already plotted. It'll just be, oh, no, it won't, because because I'm dividing by m, sorry. This is more complicated. This is looking down at successively smaller points on that plot. But okay, this is a pretty wild one. I wonder what that one is. Let's figure out what that one is. That one is very boring, the 4th one from the end. So let's just go, tell you what, why don't I do this? Why don't I actually make this into a table? So let's say, let's do this, 180 over m degrees, and that. And let's then make that into a table here. And let's, what do I want to do? Frame goes to all. Okay, oh, and then I wanted to do the thing here. I wanted to say full simplify of that. So I want to try and make this as, quote, simple as I can. Where did that go? What did I do here? Oh, it was not that. It was a different thing. I used function expand. Okay, there we go. All right, so that real crazy one is 180 degrees over 17. So that thing, though, that's actually a famous one. That is a famous one. Because that one has to do with the construction of a 17 gon. But what you see anyway is this really complicated mess, which is the formula for this. So actually one question that we might ask is, if you've got an equation, let's say you've got an equation like x squared plus 5x plus 1 equals 0, right? You probably know that you can solve that equation just by using the quadratic formula, right? Okay, there you go. There's the quadratic formula. So the question is, if you had another kind of equation, let's say I have this, instead of being a quadratic equation, I have it be a cubic equation, what happens? can I still use, is there still a formula for the answer? Well, in this case, it's considerably more complicated. Let's see if I can, let's see if I think, let's see. How do I get this to show us the formula? Actually, I can do this. Okay, so there's the considerably more complicated formula for that cubic equation. What about a degree 4 equation? Well, I could do that too. Did I get this right? Yeah. Okay, there's the degree 4 equation there. And that's considerably more complicated, right? Now, if we just want to know what are the numerical values, we can just say, what are the numerical values? Okay, that's easy enough. We can find out what the numerical values are. But if we want to work it out exactly in terms of square roots and things, it's really hard to do that. And so a result in math that was gotten in the 1830s, actually, a long time ago by a chap called Galois originally, was that you couldn't have a formula for anything of degree more than 4, a general formula that would always work. But actually, there's sort of a footnote to that because it's a general formula involving square roots, cube roots, fourth roots, et cetera, et cetera, et cetera. If you allow other kinds of functions like sine, or a little bit more exotically, like things called elliptic functions. So, by the way, in case you don't know it, if you know the perimeter of a circle, right? Everybody knows the perimeter of a circle, yes? Perimeter of a circle here should be, oh, come now, what am I saying? Perimeter of a disk, maybe, is 2 pi, right? People know that. Okay, what is the perimeter of an ellipse? So an ellipse is like, right, if I make an ellipse here, if I say, let's see, I say disk centered at 0, 0, and I have its, okay, so there's an ellipse. So what's the perimeter of an ellipse? You might think that was a pretty elementary thing to work out. It turns out it's not. It turns out that the perimeter of an ellipse is not 2 pi. It's actually something that, let's see whether we can work it out here. It's something rather exotic. It's a thing called an elliptic function. And that's just like the sine function is defined as being the thing that basically tells you the height of that line as you go around a circle. So this elliptic function is basically defined as the thing that tells you the perimeter of an ellipse. And in general, if we say our ellipse has its semi-major radius, the big radius here, of A, and the semi-minor radius, the little radius of B, that's AB here, for example, and that's the formula for, it's kind of an exotic formula that you don't typically learn. I don't know when people learn that formula, maybe never, but that's the formula for the perimeter of an ellipse. And if you use those functions, elliptic functions, you can actually write down a formula for the solution to quantic equations. And degree 5 equations. So it's kind of a thing where even though you can't work out the answer in terms of square roots and cube roots and things like that, there is still a perfectly reasonable mathematical formula for this. You're asking, why does it not work? Why can't you work it out? Actually, it's a little bit complicated to figure out why you can't work out the roots for degree. It uses the main way to do it uses this a thing called group theory, and I don't think I can really give you an elementary version of that. Okay, so what's his name? Gosh, I've already forgotten his name. The chap who does 3 blue, 1 brown. He's a good guy, and apparently he has a video about this. Actually, let me talk about what you can work out and what you can't work out. Okay, so you might think, okay, so let's say, let me show you an example of some things you can work out, things you can't work out. So this is, let's say we're going to have a very simple setup for a program. So this is a program where this is kind of a math-like thing where you just have a bunch of cells. Each one is either 0 or 1. It's kind of one of my favorite kinds of systems, a thing called the cellular automaton. And let me show you what this does. If I use that rule, we're gonna understand hopefully what this rule does. Okay, so let's see if we understand what this is doing. Okay, so the idea here is this rule is a lookup table that tells you for any particular cell here what color it should be. You're going down the page starting off from this thing here. So if we look at this 3 cells here, it goes black, white, white. So let's look up black, white, white here. Says the cell underneath goes black. Okay, so that's the rule for this that makes this picture. So we can, that's really simple rule, produces the really simple pattern. We can easily predict what's this pattern going to do. It's just going to be a big flat piece of black. Okay, let's try a different rule here. Okay, let's try this one. All right, so here, instead of it being just flat black, it's a checkerboard. Again, pretty straightforward. Okay, so is there anything else that can happen? Well, let me show you another example. So this is another rule, and this one, if I run this one, you'll see it makes a slightly more complicated pattern. Probably you can guess what this pattern is going to do.
A Sierpinski triangle.
Yes, it is going to be a Sierpinski. Let's try running a full Sierpinski here. Let's go 400 steps, for example. And yes, it will fill in, and every little piece of this pattern is like the whole thing. Okay, actually we can kind of understand what this is doing. If you want to figure out what this is doing, if you look at these this thing, there's a sort of mathy way to understand this. If you take the 2 sides, let's call them A and B, the first cell on the left, the cell on the left, the cell on the right. Then if you take, if you think of them as numbers, black is 1, white is 0. If you take the sum of those numbers mod 2, then that gives you the results here. So every time the 2 cells are the same color, you get a 0. Every time they're the opposite color, you get a 1. And that gives you this pattern. That's actually, it's like Pascal's triangle, but worked out mod 2. Well, okay, so next question is, well, what happens if you use different rules here? So there are obviously lots of different rules. There's 256 possible rules that you can use for this in this setup. So let's try doing another one of these little experiments and just work out what happens with all of those rules. This is an experiment I did a long time ago, and it's my kind of all-time favorite computer experiment, and it's really pretty trivial to do, as we are about to see. But let's just see what happens as we try all these different rules. Okay, and we might think, okay, we've got a really simple rule. Each one of these is a different rule. Okay, so this is a particular rule, and this particular rule, you start off with a black cell here, and you get just these vertical stripes and horizontal stripes, and so on and so on and so on. Okay, this is my all-time favorite. This is a thing called Rule 30, and it doesn't do something so simple. So let's take a look at what it actually does. So we can let's go here, and let's pick up those there. Let me just show you this thing. And this is in the big question is, what's this going to do? Okay, so there's the rule for Rule 30. Let's see what it does for a few steps. Okay, there it is. And let's try just running this. Let's try running that instead for, let's say, 400 steps. Get rid of the mesh and ask what it does. Okay, so there's a little bit of regularity here, but it's surprisingly random what happens. And so the question here is, in this kind of what can you figure out with math type question, is if I ask you what's this going to do after 1 billion steps, can you figure that out? Clearly you could figure it out by just running it for 1 billion steps. That would be a lot of computer effort. That would be oh, actually that's about as much computer effort to just run it for 1 billion steps. That's 10 to the 18 computer operations, which is a lot. But so we could clearly find out the answer by just running it for 1 billion steps. The question is there a way to kind of shortcut there? Is the way to jump ahead and figure out what the answer is without having to try all the steps? And the answer, so sometimes, you know, if I look at something like this, you can pretty much look at it and say, oh yeah, I can figure out what's going to happen. This one, you can't really do that for it. And the question is there a way of using some kind of math to work out what the answer is going to be without just following all the steps? Okay, so the answer is no, there isn't. The answer is sort of a fundamental fact about the way that math and computers and so on work, that there are things like this where you can set up the rule. The rule is something very simple, but yet when you run it, there's no way to find out what it will do, essentially, other than by just watching what it does. So let me give you another example here. So there's another one of these that's kind of a fun one. That is rule 110. And if we look at this one, you might ask, it only grows on the left-hand side, so it doesn't bother to show you the thing on the right. So you can see this little structure that's being produced here. So the question is that going to die out, or is it going to keep going forever? Okay, what do we think the answer is? Well, let's try running it for 1,000 steps, see what it does. Okay, it's running, it's running, it's running. Is it going to die out, or is it going to keep going forever? Well, we don't know. We can keep running it. How long do we have to run it for before we know? Is there any way we can know in advance how long we're going to have to run it for? That's 2,000 steps. Okay, still funky things are going on. Look at all those weird little creatures that are being produced there. Finally, after, I don't know what it is, I think it's about, I forget, maybe, let's try 4,000 steps. Okay, at 4,000 steps, we can see that, okay, it finally dies out and it's just giving a simple structure there. Okay, but it took us actually running it to find that out. We didn't have a way to just sort of jump ahead and say, what's it going to do? If I changed the initial condition here, if I changed what it started from, let me try changing that. Instead of 2,000, let me just do a version of this with, let's say, I don't know, 11101 here. I'll get a different pattern, and we won't know, it'll be a different question whether it's going to halt or not, whether it's going to stop or not. And this question, so we got this simple rule, we run it, the question is, what's it going to do? And so if we ask the question, what is it going to do in the end after an arbitrarily long time? Is it going to stop? Is it not going to stop? You know, we have essentially a mathematical function here. We feed it in what the input is, you know, what the initial setup is for this thing. And then the output is supposed to be, let's say it's supposed to be 1 if it halts, 0 if it doesn't. Halts meaning it dies out, and 0 if it doesn't, let's say. Okay, so the question is, can we compute that function? And the answer is, well, we actually in general can't. We never know how long it's going to take us to work out the answer to that function. And so that's actually a phenomenon that was originally discovered in 1931. It's this in a much more complicated version called Gödel's theorem. And this is basically a version of Gödel's theorem that basically tells one that just because you know the rules doesn't mean you know what's going to happen. And in general, if you ask a question like, what's going to happen in the end after an infinite time, there may be no finite way to guarantee to answer that question. So remember, with solving equations like quadratics, cubics, quartics, quintics, and so on, the question was, could we find an answer in terms of square roots, cube roots, and things like that? And in the case of quintics, we couldn't find an answer in terms of those roots, but we could find an answer in terms of elliptic functions and so on. Now the question here, in this more kind of sort of program type setup is, can we find any answer at all in you know, with any method that we use? It doesn't matter whether it's elliptic functions or anything else. Can we find any method at all to get the answer? And the result is no, you can't. And that's sort of a basic, very important result in kind of math and computer science. It's actually a result that, well, people thought that these cases where you couldn't figure out what was going to happen in any sort of finite way were really rare, that there were weird things that you had to look very carefully for. One of the things that I found actually is that that's not the case, that actually it's really pretty easy, like we found an example here with this cellular automaton. It's pretty easy to find cases where if you pick the wrong problem, so to speak, if you pick this problem, you won't be able to answer the question at all. You'll be able to pose the question, but there's no finite way to answer the question. So a thing you might ask then is, okay, so does that mean that math is going to get stuck? Because maybe the questions that we want to ask in math will end up being a bunch of these questions that just we can't answer. And so actually it's a big question about math, why math has been able to get as many answers as it has. So one of the things that, when we start thinking about, when we start doing math, we can say, let's try and work out a bunch of math theorems, right? We can just start saying we've got some ways of working out math theorems, some axioms for math, like things about geometry or something like that. And we say, let's just start working out all possible theorems. So there's a question, what happens if you do that? Or if you just pick something which you might say might be true, is it likely to be the case that the thing you pick will be one where you can get the answer using methods from math? Or is it something which is going to have this problem of being undecidable? And so it's one thing that actually it's sort of an interesting question. First thing is that the fact that math is hard, the fact that it's not trivial to go from kind of the rules for math to work out every problem in math is a consequence of this same phenomenon, that it's hard to know what's going to happen without just running the rules. The fact that math is hard is a consequence of that sort of basic fact about computational systems. But then there's a question of, well, if you pick questions in math, are they going to be solvable at all? And actually, there are a bunch of famous questions in math that I suspect will have the feature that they actually aren't solvable at all, that there isn't a finite way to get an answer to those questions. Sort of a big issue of why the math that people have chosen to do is as successful as it is. And that's an interesting question about philosophy of math, which I think I actually now know a bit more about the answer to. Somebody was asking here, can you tell if there's a rule? So for example, in something like this, if you know you're looking for one of these cellular automaton rules, it's pretty easy to tell that there's a rule, because you just go in and look at every cell, and you just say, you look at this lookup table, basically, and you say, given these 3 cells, what happened next? Given these 3, if I see 3 black cells, it's going to make a white cell. Let's check. Every single 3 black cells, it makes a white cell. Great. Okay, that's good. We check for all the other triples of cells. If they all work, then we know we have a definite rule. All right, we are getting close to running out of time. So I think we've been jumping around a lot about a bunch of different things. I'm happy to try and talk about whatever people are interested in here. By the way, if you guys are, I should give a little ad for, I've been doing, since there's been a pandemic going on, I decided I would do a kind of fun educational thing. So every Friday afternoon, I've been doing kind of a general Q&A about science and technology and other things, which people seem to like. And you can find, well, many episodes of it probably now on YouTube or on podcast kinds of places. But if people are interested, I tend to end up talking about all kinds of, people ask all kinds of strange questions about science, technology, etc. Here I've mostly been talking about kind of computational mathematical things. There I'll talk about general science and physics and things like that. How does Wolfram Alpha look when you sign in? Not much different. The main thing it does is, let's see, what can it do when I sign in? Let me see. Let me see if it knows me. Let's hope it knows me. It's hard to know if it knows me. Let's take a look. Let's see, how do I sign in here? I think we've changed the way this works. Okay, there we go. There's a signed in Wolfram Alpha. And the main thing that it does is it gives you like step-by-step solutions to things. So if I say, if I'm going to do calculus and I say, integrate x log cubed x, which I actually might be able to do by hand myself even. It'll show you things like how to do that step by step. It'll also let you run longer computations than when you're not signed in. A question from Jason here. Did I work with others to create Wolfram Alpha and the language? Or was it mainly a solo project? It's a very big project. This is, by the time you're trying to cover all these different kinds of things, of chemistry and food and nutrition and history and all those kinds of things, that's a very big project. No, I run a company that has, it's actually a fairly small company. It's about 800 people working on building this technology. And so there's a bunch of, yes, it's a lot of people, very talented people, and we've been working on it for a long time. It's my main responsibility is, other than CEOing the company, is figuring out kind of the design of how everything works. So we're just about to bring out a new version of Wolfram Language. It'll come out in the next few days. And so a big thing I've done is figure out, what should all these functions be? How should they be set up? What should they be called? All those kinds of things. And the thing that was so actually we live stream a bunch of the design meetings that we have talking about how that works, but that's one of my main activities. Question from Jelly, is this math or technology? Well, I don't know, what is math? I think I've worked a lot on the philosophy and foundations of math, so I should be able to give a good answer to the question, what is math? And it's complicated because it's like you find all these different theorems, and let me show you an example of something. Let me see, here we go. Yeah, this is, you've probably heard of Euclid, famous mathematician from antiquity, who figured out a lot of, wrote sort of down the definitive collection of theorems about geometry. Actually, he wrote 465 theorems. He had 10 axioms, kind of assumptions that he made, and then he worked out 465 theorems. And I just recently figured out the whole kind of structure of what theorem led to what, and so on and so on and so on. He could have picked an infinite number of possible, any of an infinite number of possible theorems. He actually picked 465 of them. And that's kind of a big part of the story of math, is how do you pick out from all the possible things that are true about geometry, how do you pick out the ones that actually seem interesting to tell people about? And that's a big piece of the whole kind of math story. Somebody's asking, what inspired me to start this project? Okay, I can tell you a little bit about that. So when I was about your kind of age, probably, I got really interested. Well, I was interested in the space program, which was big back in the 1960s when I was a kid. And I suppose it's big again now, finally. So I used to follow kind of all of these deep spacecraft and all those kinds of things. And I got interested from that in kind of how does all this stuff work? And that got me interested in physics. And so I started learning about physics. And I guess when I was, probably I started even writing stuff down about physics and so on. And then I realized that I wasn't very keen on kind of doing exercises in books. And I just learned physics by reading books. And so then I started trying to figure out, well, could I figure out answers to physics questions that weren't exercises in books? And by the time I was 14 or 15 or so, I figured out, yes, I could figure out some answers to things that people didn't seem to have answered before. So I started publishing papers about physics and things like that. But one of the things, so I was very enthusiastic about physics, but one of the things about doing physics is that if you sort of try and do research physics, you end up having to do lots of kinds of mathematical calculations, and I was not so keen on that. And so I thought, this mathematical calculation stuff is really boring. There's got to be a better way to do this. And what I realized is, well, actually, you should be able to use a computer to do this. At the time, computers were very much more primitive than they are today, but I started using computers to try and do mathematical kinds of things. And basically, that's what ended up, in the end, leading to building Mathematica and Wolfram Alpha and so on. Actually, very recently, I've gotten back to physics, and so kind of a big deal that one of the sort of big surprises from looking at these kinds of little programs And what they do is that from even a very, very simple program, you can get very complicated things to happen. So that kind of makes you ask the question, might there be a little program that's kind of running our whole universe? And the answer is, to my big surprise, that we figured out a huge amount about this. And the answer seems to be basically yes. And this is a kind of, I'm not going to talk about this in detail here because it's a long, long story. But this is about kind of, it's kind of a rough summary of kind of how we think physics works. And it's kind of a story of, if you look at space, and you look at very, very, very small scale, you say, what is space made of? It's kind of like if you ask for, water or something, what is water made of? Well, if you look at a small enough scale, you'll find out the water is made of discrete molecules. And the thing, people in physics haven't thought that's how space works. But actually what we now think is that that is how space works, and that at a very, very, very small scale, at a trillionth of the size of an atom, roughly, space is actually made of discrete things. And those discrete things are just kind of connected together in a giant network. And when, and kind of all the things that we see in physics are consequences of things that happen in that giant network. And the sort of big deal in the last, 6 months or so has been finding out that we can indeed reproduce all kinds of features of physics, including all sorts of things about relativity and black holes and quantum mechanics and quantum computers and all this kind of thing from this kind of very low-level machine code of just little points in space interacting with each other. So that's kind of a pretty exciting thing. Okay, name of the Friday afternoon program. Well, let me go find it. Good question, good question. I should know, but let me go find it. I'm going to have to look on my own website here to find it. Let's see, if I go to podcasts, is that right? Well, okay, on this, I have to admit, I have not looked at this page. On this podcast, these are podcasts, these are previous episodes, but this is Q&A for kids and others. And I think it must be on, it's broadcast on Twitch and YouTube Live and things like that. So you should be able to find it there. Let's see. Question, did you have anyone who supported you throughout this whole journey? Well, I'm an old guy now, so I've been, I would say that lots of people, I mean, I've been running a company now for 34 years, and the people who work at my company are an important part of the story of how the things I'm talking about have gotten done. In more recent times, my kids, I have 4 kids who are, I guess the youngest is about a little bit older than you guys. They help keep things interesting and teach me things and so on. Let's see. Somebody's saying, I thought Twitch was a gaming platform. Well, it originally was something even different from that, but it's partly that, but it's also a place for live streaming all kinds of things. So for example, we live stream, let's see if I can find it here. We live stream. See, I'm now trying to navigate my own website. Yeah, so this is one of our, I've done 415 episodes of live CEOing. This is about designing how this language that we build actually works. It's kind of yeah, okay. Let's see. Can the simple program running the universe find new math? That's a more interesting question than you might think. If it's running the whole universe, it makes everything that happens in the universe. So it makes every mathematician, it makes all of us, it makes everything. So in that sense, yes. But actually there's a different sense in which, this is kind of going to get us into something a little bit complicated, but let me explain quickly explain one thing, and I do need to run off fairly soon here. Okay, this is another big project of mine. This is a big book called New Kind of Science, which you can find on the web. I will put, actually, if people are interested, this is I would say, quite accessible. I put a lot of effort into making it easy for people to read. But someplace down here, it talks a bit about math. And so let's say you're trying to do some math and you're trying to prove that some particular thing, let's say this P blob Q is equal to Q blob P. And you know certain facts about A blob B is equal to A, et cetera, et cetera, et cetera. You know these various facts. The question is, can you sort of put together the puzzle pieces to show that A blob B is equal to B blob A? Okay. And so that is like asking, that's kind of like asking about a mathematical proof. These are the axioms for a mathematical system. And this is asking, you know, can I find a proof in that mathematical system of this fact is equal to this fact? So it turns out you can think about, let's see if I have an example here. It's not a particularly good example. I've got better examples. Okay, so this is basically showing, this is sort of all the possible proofs in effect that you could, every path here is a proof. Every time you can get from this thing to, let's say, this thing here, that's a proof in some sense that this is equal to this in some mathematical axiom system. And so this question of how you make math is kind of a little bit the question of what possible paths are there through one of these systems that make something complicated like this. Okay, so the big, crazy, weird thing is that there is a kind of one of those complicated branching things that is a core piece of how we think the universe works. It's actually a core piece of how quantum mechanics works. And the structure of all this branching and how things merge and branch and so on, that can be thought of as proving a bunch of math theorems is actually also the way that, well, the fact that essentially a bunch of math theorems are true is the reason, this is really weird, but it's the case, it's the reason that, for example, different people think that the same things happen. So in other words, that it's the reason that, again, there are essentially theorems that say what the world seems to look like to this person is going to be equivalent to what the world seems to look like to this person. And those theorems, sort of a huge collection of those theorems that are basically what make physics seem the way physics seems. And so there is some very bizarre sense in which sort of this theory of physics kind of makes all of mathematics. And actually, there's even a more, this is like super abstract math that is kind of at the very outer limits of what math people now understand. There is a sense in which kind of the ultimate limit of what we see in physics is the same as the ultimate limit of what we see in math. Because in math, you can ask the question, okay, we've done a certain amount of math in the history of our species. There are about 3 million theorems that people have written down and published in math papers. The question is, if we take the limit of an infinite amount of math that's been done, what will that look like? What will happen after an infinite amount of math has been done? Well, actually, we can now give part of the answer to that question. And it's surprisingly similar to a bunch of questions about physics. Let's see. Oh, people are asking about Turing machines. Jelly was asking, is this meeting, that was probably the science Q&A for kids and others? Yeah, there's an and others part there. And I think we've done surveys and some fraction of the audience is kids and some fraction is not kids. Question, how to edit files in Wolfram Player. So the Player is a desktop application that lets you run these notebooks. If you want to edit files, well, you can either actually get a proper Wolfram desktop program, or you can use the cloud and use the Cloud Basic system in the cloud. Someone's asking about Turing machines, probably not for today. I will say that yeah, I'll give it, okay. I think I've got to give a few more ads. Gosh, there's all kinds of educational things that we end up doing. So I think I have to give another ad. For people who are at high school age or going to be at high school age. We do the summer camp every year. This year it was virtual. Next year it's going to be kind of a hybrid virtual, non-virtual. And it's a 2-week thing where people do all kinds of projects. These are some of the projects from this last year, and something I recommend. Actually, I have been doing something for middle school kids, but I have been doing it as a physical thing in Concord, Massachusetts. And I thought you guys would turn out to be physically in Lexington, Massachusetts, which is just one town over. And so then I would have advertised that. I've been doing it right now, kind of virtually, but I think the audience is still pretty local here. But if people are interested in that, they can contact maybe the organizers of this who can contact us. And I think we've because it is a natural phenomenon that people of a certain age get older. So my population is thinning out. So there are probably going to be some more slots for people who are interested in that. And that's a kind of a more interactive. Well, sometimes it's writing code, and sometimes it's doing other kinds of things. All right, I think I probably exhausted what I can say here, and I hope you guys found this interesting, and I mean, look, I'll put yeah, I have a public email address which you can if people have science questions don't work so well, but if they're kind of a kind of profound life question or something, that's a good it's a good email address to reach me at, and I'm often game for answering questions for kids and so on, but typically not. If you want to ask science questions, come to one of the science Q&A things. That's a much better venue, because then I get to answer the question for everybody, not just for one person. And I said I would upload this notebook to the cloud. So let me go ahead and do that. And then we publish this to the cloud and then send you guys the link to it. It's gotten a little bit bigger, so it might take a little longer to publish here. No, there we go. All right, send the link. There you go. So you can play with it there. I need to go off and prepare for this, because I'm not finished. I've been trying to write a history of what happened 100 years ago when this thing was discovered, and I am about to finish, but I am not quite finished, and I have to finish before tomorrow. So that is my homework, and I better go off and do my homework. Maybe you guys better go off and do your homework, depending on what time zone or place you're in. Anyway, it was nice to chat with you all, and good luck with everything. Okay.
Thank you for giving this talk. It was very nice to hear everything you had to say, and it was very kind of you to give up some of your time to give this talk to all our students.
Well, thanks a lot. See you all. Bye-bye.
Bye-bye.